So how this a dye sensitized solar cell works? So it is again basically like a thin film solar cell, but the working of the solar cell is a little bit different from traditional this first generation PN diode based silicon solar cells. So what we have here is, so in the figure what you can see is, so normally you have a substrate which is transparent and conducting. So on the left, extreme left, you see that. So let me zoom it in. So on the extreme left, you have this conducting substrate which is as transparent as well, so that it allows light to pass through it. And then you have a, a semiconductor which is typically a wide band gap semiconductor which acts as a charge, which takes the charge and participates in the transportation of the charge. And the most important part, what you have is here a dye or a dye molecule, which acts a as a medium which generates your charge carriers. So in PN diode based systems, so like if you take a silicon photovoltaic, so your charge carrier generation and transport both are done in the same device, right? So the PN diode itself, you have a generation of uh, charge carriers, so electron and holes, as well as this PN junction diode, you acts as a charge transport medium as well. But in this case, what you have is a different material, a dye. It's like a molecule. It can be organic or it can be inorganic. Uh, and that basically acts as a source of charge carriers. So when photons they fall on the this dye molecules, so they excite electrons or basically charge carriers, and these charge carriers will immediately they will jump to the conduction band of the semiconductor, wide band gap semiconductor, that is uh, deposited on your transparent substrate. And then, so basically this electron which is created due to the photon will be transported to the semiconductor, to the conducting substrate, and then through an external circuit. So this is your external circuit. Through it, it will uh, go to the other part of the electrode, so that you can get some output current or output voltage from it. And so this is one part, but you also need to have a counter electrode and electrolyte. So this is like a mixture of, you have a PN diode plus some kind of electrochemical cell. Both our devices are present in the same this dye sensitized solar cell. So in that sense, it is a little bit different from your normal silicon photovoltaics. So in normal silicon photovoltaics, so you have the charge carrier generation and the transport happens in the same device, but here the charge carrier generation is done by a sensitized, dye sensitized molecule, and the carrier, this charge carrier or the charge transport is taking place via semiconductor, a PN diode, as well as some electrolyte that is present in the device. So this electrolyte, so you will look at individual component one by one. So what are the component? So the first component is you need to have a transparent conducting oxide. So typically this material is fluorine doped tin oxide or indium tin oxide. So these are the typical substrate materials that are used in the solar cells. So what are the properties they should have? They should have really high transmittance and high conductivity. So these are the most important parameters for when you choose a substrate in this solar cell. So you need a high transmittance because the light should pass through the substrate and should go to the reach your dye molecules. If the substrate is itself reflecting or absorbing, so all the light or all the photon doesn't reach the dye molecules, and therefore you will not get enough photocurrent. So this photoelectrons, let's say. So to excite this photoelectrons, so you need this transparency. So which is typically like above 75% or 80% in this case. And of course, you need a high conductivity because they should also participate in the charge carrier. So they are connected to the external circuit. So they are acting as like something like a contact as well. So therefore, you have to make them conducting. The second component is the working electrode, which is the short form is WE. What is the working electrode? That is basically the semiconductor which is collecting the charge which is generated in the dye molecule. So once this charge is generated, so immediately this working electrode kind of captures it or takes this electron, and typical materials that are used are this white band gap semiconductors, basically titanium dioxide, zinc oxide. Okay, so these are the materials that are typically used, and normally you deposit as a thin film form on top of these oxides on this transparent substrate, and so this is like a thin film form of these materials. And typical band gap is like 3 electron volt or maybe a little bit higher than that. So they're wide band gap semiconductors. And most promising material so far has been titanium dioxide, so which is actually extensively used quite a lot. So in the beginning, this zinc oxide. So when this dye sensitized, so it was not, let's say, called a dye sensitized solar cell, but the concept was it was existing in 1960s or 70s. So in those days, what researchers were doing is basically you can take so one dye molecule is like chlorophyll you have on your leaves. Okay, so which uh, normally you take the, I mean, convert your solar energy to some form of other chemical energy and so on. So people used to use these natural dye molecules extracted from plant materials, mostly from plant materials. Uh, you can coat it on semiconductor and use it for this like PN diode kind of junction they used to make. Okay, so but at that time it was not like really used for solar cell application. So sometimes this dye-sensitized, this kind of design is also has a name. It's called a, I think it's a Gretzel cell, so which was kind of explored extensively by scientist named Gretzel and his co-workers. They worked quite extensively on this kind of dye-sensitized solar cells in 1988, 1991, in those times. So they really developed this field uh, extensively, and that is why the name is such. But the concept normally used to, it was there until I mean before 19, like between 1960s and 1970s. So you need a electrode, working electrode. So you need a substrate, then you need a working electrode. Yes.
Sir, which band gap range is most suitable for the solar cell application?
Oh, for the yeah, we will talk about that. So just in a moment, so you'll understand why I am saying that we need a wide band gap semiconductor. Uh, so the most promising is titanium dioxide so far, which is really used almost in all of these in this dye-sensitized solar cells. And typically what you expect that the semiconductor material should absorb only a fraction of sunlight, so mostly in the UV region, because you want that the absorption should happen in your dye molecule. So the dye molecule absorption spectra should be such that it should absorb as much as photon as it can. So therefore, you need this wide band gap semiconductor, and typically it is this band gap is higher than 3 electron volt. So for titanium dioxide, it is typically like depending on the structure, so it can be 3 electron volt or 3.2, like something in between that. So you need typically a little bit higher band gap so that your most of the absorption or generation, this photoelectron generation happens in your dye molecule. Okay. So this dye molecule is like a typical, it can be organic or inorganic molecule. So, so so I wrote here is this quantum dot, but typically this di quantum dot is not a di molecule. But if you look at it, it also has like absorption in different wavelength regions in the visible range. So it also kind of a color kind of material. So although quantum dot is not really part of the dye sensitized solar cell. So quantum dot based solar cell is a different solar cell device itself. But these dye molecules are typically, as I said, they should absorb the maximum photons and create the as much photoelectrons as possible. And typically you coat these dye molecules on your semiconductor material, which is, let's say, titanium dioxide. So you coat them, so basically they are dissolved in some solvent, okay, and then you dip your semiconductor coated substrate in it, and then over a certain period of time, so these dye molecules will bind to the semiconductor surface. So typically they will form a covalent bonding, so that they can be tightly anchored on these surfaces, on the semiconductor surfaces, and then also a efficient charge carrier transport can happen between your dye molecule and your semiconductor. So normally the people also use or talk about this light harvesting efficiency of these dye molecules, so LHE, because so these devices or these molecules are basically acting as light harvester. Okay, so they are just collecting the photons and creating this uh, photoelectrons. So they are, so that means the higher this light harvesting efficiency is, so better it is for the solar cell. So a dye molecule should satisfy certain should have certain parameters so that it can be used in these solar cells. So it should be a luminescent. So I already said, so they have a wide absorption spectra, so covering from infrared up to UV visible range. And typically this excited state of, so now when you excite the electron from the ground state to the excited state, normally in chemistry there is a term called homo and lumo gap. This, so two, so one is a highest occupied molecular orbital, and the lumo means lowest unoccupied molecular orbital. So your, so this LUMO is basically your excited state of the dye molecule, and this excited state should be as close to the conduction band of the semiconductor. So, so if it is really close to the conduction band of the semiconductor, so when the electron is excited, and now when it wants to get de-excited, so it can immediately go to the nearest lower energy level, which is the conduction band of the titanium dioxide. Okay, so this is one of the most important parameter for the semiconductor material as well as for the dye molecule as well. So of course, since it is kind of immersed in a electrolyte, we will see what is the role of the electrolyte here. So the, since it is immersed in an electrolyte, so it should be chemically stable as well. And here is an example of one of the dye molecules which is commonly used quite a lot. This is a ruthenium based like a metal complex. So you can see a lot of chemistry is going on here. So a lot of organic components or benzene rings that are attached to it, and also some other carboxylic group and other groups are also connected, so that so this chemistry is done to increase or increase the light harvesting efficiency of the dye molecule. So this is like also one of the most common dye molecule, this ruthenium based complex that is actually used. Okay, so another component is the electrolyte, or it is also known as a redox couple. So what is the role? So it actually helps in, so when the dye is getting, this electron is excited, and then now the electron is gone to the semiconductor, so the dye molecule is in a kind of oxidized state. So now one needs to bring it back to a normal state or reduce it, so that it can again participate in the excitation, photo electron excitation process. And how do you do that? And that is where this electrolyte plays a role. So what the electrolyte does is basically reduces uh, your dye molecule, so that again it goes back to its ground state, and then again, so this is known as a regeneration of dye. So this helps in the regeneration of the dye, because the dye molecule, once it is excited and oxidized, so you have to bring it back to reduce it, so that it can participate in generation of electrons again. And this electrolyte also, so like any electrolyte, so where inside that you have ionic spaces, so in which your ions should be able to move, and these ions normally will carry the, or will help in the reduction of the dye molecule. So therefore you should have an efficient way of moving of these ions inside electrolyte. So the diffusion should be done faster and efficiently. So this is an efficient transfer of ions or diffusion of ions through the electrolyte. It should of course be non-corrosive. So if it is corroding your semiconductor material or your dye material, or even let's say somehow it reaches the substrate. So if it corrodes it, so it is not good for the device. So because in most of the solar cell applications, one parameter which is like how long it can act or operate without getting any without or with a minimum maintenance. So in that way silicon photovoltaics are really attractive. So you can actually they can operate with a very low maintenance for like 25 years, 30 years, okay, or maybe 40 years. For that time span they can work. But here, since a lot of chemistry is involved, so sometimes the lifetime can be shorter here. And therefore this is again a challenge for this dye sensitized solar cell. And of course, the absorption spectra should be different from the dye molecule. Of course, it should not absorb the light, because all the light, whatever, should go to reach the dye molecule. And again, it should also have a thermal and electrochemical stability. So the example of this ionic or this electrolyte, that the ions, so it is a sometimes iodine based electrolyte is used, or bromine based used, so cobalt also being used, or ionic liquids are used. So mostly this, but most of the time, or the which is really used quite a lot, is this iodine based electrolyte. So that means you have a reduction and oxidation of iodide to triiodide, and vice versa in the electrolyte, which basically helps in reduction and reduction of your dye molecule. And the last part is your counter electrode, which is nothing but it collects the electron from the external source, which is generated in the semiconductor and in the substrate, and it flows through an external circuit to the electrode, back electrode, or a counter electrode, which also helps in reduction reaction of this iodide to triiodide, and basically plays a role in the electrochemical cell. And typically what is used is platinum. Of course platinum is a bit expensive, but this is used quite a lot. And nowadays people are also exploring this carbon based materials as well. So in a simple way one can understand that. So you have a light which is shining on a, this is your substrate, so this is your ITO substrate, let's say, and then you have the titanium dioxide, so dye sensitized molecule. So what you do is you basically excite a electron from the ground state to the excited state. So we can write here S goes to S star, and then this electron will jump to titanium dioxide. So then what you have is S star, let's say plus, and E minus, and this E will flow. So this is can be your platinum. So this electron will flow through the external circuit, and then you have the electrolyte here, so which basically will oxidize this S plus, will then again get oxidized via the electrolyte and go to S. Okay, so this is the basically your is the way how this sensitized dye sensitized solar cell would work, and it is basically a mixture of your PN diode plus electrochemical cell. Okay, so what are the role of nanomaterials here? So what you have is like for example this titanium dioxide. If this titanium dioxide, instead of taking thin films, normally what people take is nanoparticles of titanium dioxide, and typically like 20 nanometer in size. And what that helps in enhanced surface area, right? If the surface area becomes higher, because we are using now nanoparticles, and therefore we can incorporate a lot more dye molecules in the system. So if I take a thin film, so I have like a limited number of dye molecules, but now I can put a lot more dye molecules in it. They will attach to the surface of this nanoparticle, so I can enhance the efficiency of light harvesting. So I can have many more molecules which can participate or generate this photoelectrons, so which actually helps or increases the efficiency of the material. So basically this role of nanomaterials is to help in increasing the efficiency of the solar cells. So typical efficiency like in these solar cells is like 7% or 10%, or nowadays people claim around maybe 11 to 12%. So it is not much, but still it is like one of the cheaper way to prepare a solar cell, very cheap compared to silicon photovoltaics. Uh, and also they use yeah, I mean these abundant materials, uh, and very, very easy to synthesize, uh, and therefore these are like promising for industrial applications as well. But these nanomaterials actually really play a big role in increasing the efficiency of the material. So you can take a porous material, or you can take nanomaterials of the active electrode here, the working electrode. This counter electrode, nowadays people are using graphene sheets or carbon nanotubes, so that they can enhance the catalytic properties of the electrolyte, so that it can easily oxidize and or reduce, so that the charge transfer can happen very fast. Okay, that is the in that context, these nanomaterials are really playing an important